Hello and welcome back to Calculus 3. This is the second part of 12.3 limits and continuity, and we are continuing with the Calc 1 review limits. So both methods compute the limit of the function, which is the y value of the function, with their advantages and disadvantages. So pre-calculus, as I mentioned, on the left computes at the value and at the value alone, disregarding everything else, where the limit computes at every other value except at the value of interest and infers the answer. So if you have a situation where you have the open circle like this inside the function, if you are to try and compute this with pre-calculus, well, you will get does not exist, because if you extend the line vertically up, it goes through the hole and never bounces into the y. But if you take a look with the left and right approach, all of the values that you are actually computing will have their, right, and they are going towards this 14 level that we had before. So anything before and everything after will have the y values, and you can see that they actually produce the answer. So that's the essence of the limit. The limit computes the y value, but it computes it in a different way, by computing infinitely many points around the point of interest. Now that, for Calculus 3, gives us a little bit of an issue for computing, because the limit is still going to do the same thing. It's computing now the z value. So we are going to have that the limit as x, y is approaching some fixed point a, b, which is on the floor of your function in terms of f of y, which is z, right there, is equal to some number L. So technically this is what we are looking at. Now, what does this mean? Well, just like in Calculus 1, you are computing z. So if you have something that is really basic without any extraneous issues, problems, whatever, you have limit point xy going to, let's say, 0, 1, and you have a function x squared y minus 3, whatever, right? You will get answer negative 3. Because when you plug in x equals 0 and y equals 1, you simply compute negative 3. So this is technically a point 0, 1, negative 3 in space. And you can calculate all of the z values, and you will get whatever the shape that the function produces. So again, we have this duality, that the pre-calculus part, where you just plug in the number, and then you have the limit part, where you compute everywhere around. Well, it's much trickier now for Calc 3 to deal with the limit when you want to compute it, and it's not clear what it is, because of the sheer amount of ways that you can use to approach the point in 2D. When you are, so this is now Calc 1, when you are on the number line x and you want to approach to a, you can only approach from the left, or you can approach to the right, and we call that limit x approaches a minus and the limit x approaches a plus. So, and that was it. If you have a one-dimensional plane, you can approach it from left, you can approach it from the right, and that's it. You exhausted all possibilities. But now, when you are in Calc 3, and your domain, maybe I should just do this arrow and say domain, and now your domain is two-dimensional. Imagine you have a point AB. In how many ways you can approach this point? And there will be infinitely many. And it's not just that you can approach it infinitely many in terms of the straight lines that go left and right. You can spiral in if you want to. All right? And that's the issue. So now when you have the issue of the approach, and the neighborhood is no longer, numbers to the left and numbers to the right. The neighborhood now becomes a disk of values around, and that disk is going to have a delta radius. If you remember epsilon and delta in your limit on the calculus 1, the limit definition, epsilon and delta were the ones. And now you still have epsilon and delta, but the delta now is the radius of the disk that goes around AB. And because of that, we are going to have much harder time to compute limits that are not as easy as the one we computed earlier, where you can just plug stuff in and be done. Now, what have we learned in Calc 1? We learned that if nothing weird is going on, you will simply plug in the numbers, plug in the value, and get your answer and be done. But then we also had the issue when you had 0 in denominator when you plug in which case you had to use algebra in some sense, right? Whether it's factoring, rationalizing, whatever kind of witchcraft you had to pull off to solve it algebraically, you had to do it. And then if all of those methods fail, you would resort to a graph or a chart of values. So it was very systematic. Well, now, if plugging in doesn't work, generally, just good luck. All right, that's the best, because we don't have that many methods. Now, the whole thing over here is big on when the limit does not exist, and we'll clearly look at that. But let's first write the definition, which you are responsible for, especially the honors. So what is the definition of the limit in 3D? So we have first the notation. I had this already. So point xy is going to AB of some function f of x. Y is going to be L. If for every epsilon larger than 0, there exists delta larger than 0, such that it's the same thing like in Calc 1. Such that f of x y minus L is less than epsilon whenever zero is less than x minus a squared plus y minus b squared. These are parentheses. It's just a regular Euclidean distance. Less than delta. So as you can see, this is identical formula. So as for some kind of graphic representation over here, let's go with x and y and z. And now in xy plane, I have a point AB. Now that point, as I said, around has a circle of radius delta. And that circle, now you are going to have some kind of surface on top. All right. So that circle, right, the AB is going to hit the surface and then, hit Z somewhere. Now the circle that it's around, the delta circle, creates this third-dimensional tube around which gives you a one-dimensional image. So if this point is your L, then this point over here is your L minus epsilon, and the point on top is L plus epsilon. And the radius of the circle on the bottom of the disk is delta. So observe that you have the Euclidean distance over here. The A and the B are the coordinates of, and then X and the Y are all of the numbers that are on the edge of the disk. You can make this disk and epsilon as small as you want, right? And technically what it says is that as you squeeze this circle around, it will squeeze around and it will collapse on this line. It gives you one-dimensional answer on the z-axis, which is where the answers are. Now, if you all played with electronics, then you would know that there is, instead of using electrical tape, there's this little rubber tubing that you can use if you solder two wires together. You put the rubber tubing over that. You are shaking your head, so it means you know, and use a little bit of fire, whether it's going to be the lighter or the blowtorch, and it squeezes around and it creates a very tight insulation around the exposed wiring, which you just soldered. So that's technically the first time I've seen this. You know, that was because I used to play with those things when I was, you know, the 7th, 8th grade. You have to start playing with electronics, you know, or you don't. So first time I saw this, that was the image I had. You know, just the whole tube that it's surrounded. When you apply fire to it, it just, you know, shrinks and wraps around tightly around the wire. So, but see, as this thing shrinks around the line, these two lines, which were at the edges, right, giving you image on Z, they go closer to the one and they collapse well. So squeezing here squeezes there, and you get the L. It's the same concept like in your Calculus 1, except this is in 3D. Now, issue arises when you have like to think of jumps in a function, like a cliff, right? This part over here, if you roll something on it, it will encounter the discontinuity and will drop right away. This vertical drop here has the different y value at the same different z value at the same xy point. And we know that's not allowed for functions. So it's a jump discontinuity, right? So we have, remember the infinity of the approaches. So for one person to approach from this end, we'll see the height, the level, the answer to the limit to be, let's say, I don't know, 4 feet. So answer would be 4. And the person walking on the floor would have answer 0. Well, you can't have answer 0 and 4 at the same time. So you see that when we encounter the situation that the limit in Calc 3, the limit does not exist, it's actually based on this idea that if you find a path that will allow you to get a different answer than if you use a different path, then the limit does not exist. Now, that was very simple in Calc 1. You just say left limit, right limit, they have to be the same. If they're the same, that's the limit. If they're different, no limit. Well, now, we don't have only left-right approach. Remember the spiral thing that I drew, right? The spiral thing to approach something in a circle, right? Spiraling in or spiraling out, whatever. You have that, or you can just approach as a wave, right? The sine wave coming into parabolically, whatever. Think of the function, right? So it's we also have the issues when, right, we don't have the limit. So let's first actually put, I almost forgot, the rules of limits for 3D are the same as rules for limits in In 2D from Calc 1. So limit laws. Limit laws, again, you have the sum and difference, so this is 1/2. Sum and difference law, which says that the limit of xy going to a, b of two functions, I'm just going to call them f plus g, is going to be L plus m. So let me define this. We have the limit of f of xy giving you L, and the limit g of xy giving you m. These are both xy going to a, b. Now we have the constant multiple. Exactly. Limit xy goes to a, b of cf is just going to be cl. Good morning. For the product, and is going to be limit. Remember, this one doesn't work for multiplication division. You have product rule, right? But it works for limits. So xy goes to ab of f times g is just lm, L times m. And then the quotient is the limit f over g, which gives you L over m as long as m is not 0. And then we have a power and a fractional power. I'm just going to put, let's put both, whatever. So limit xy goes to ab of f to the n is L to the n, and fractional power is limit xy goes to ab of f to the m over n is L to the m over n. Good. So those are the limit laws, and you see that they are identical to the limit laws you had in Calc 1. So now, you know, the basic limits, again, before we go with the does not exist boundary stuff. Limit xy goes to, 1, 2 of, let's say, cosine y pi minus x squared y. That's the problem. You look at this and you say, well, this can all be computed. I'm not going to get zeros in the denominator. It doesn't look like anything would be jumping around. It's not a piecewise function. So it seems okay to just plug in. So what do we have? Y is 2, so I have as the answer of cosine of 2 pi minus 1 squared times 2. I can compute that. What's cosine of 2 pi? Very good. And then minus 2, the answer is -1. So the answer is -1. What's the limit to this? -1. So plug in and done. Now, what we worry about are the boundary points and situations where we get this, the cliffs and edges and things like that. The sharp drops. Because we can't have all of the approaches work in those cases. So let's first define interior and boundary points, and then open and close sets, and then from there we'll take a look at the arguments for figuring out that the limit does not exist for these multivariable functions. So first, interior and boundary points. So we have the definition. Let R be the region in R2. R2, you write it as R squared, and it just means two-dimensional space. So this thing is your X and Y coordinate system, the whole space that coordinate system produces. R3 is clearly 3D. So an interior point P of R lies entirely within R, which means it is possible to find a disk centered at P that contains only points of R. The second part over here, I'll change the shade, I guess. A boundary point Q of R lies on the edge of R in the sense that every disk centered at Q contains at least one point in R and at least one point not in R. So 1 point in R and 1 point not in R. Now to draw this, we are going to just imagine some domain. So this domain lives in X. Here, I'll draw X and Y plane if that makes you happy. So this is our domain. It is R2 space, and this region is region R. So now I can go and find the point P somewhere and call that interior point because I am able to draw a disk, right? I can draw a smaller disk, I can draw a larger disk, but I am able to draw a disk that is not going out of the region R. All right? Or I have point Q, and Q is on the edge. So when you draw the disk, you see that there are points that are inside the region R and the points that are outside of the region R. So that's the boundary point. Now you see, it has to be exactly on the edge to work. Remember, in mathematics, you can zoom infinitely far. So if you say, but how about if I just, really close and I can't squeeze the disk? Yes, you can. The disk has when I draw here, it takes pixels. If I push light, if I push hard, I'm not changing thickness of the pen. I just use the force, and the thickness adjusts how hard I press. But you can definitely see the thickness difference between the two, or all three, right? And clearly there is the thickness to this line, but this arbitrary disk has no thickness of the line. It's infinitely thin. So you can't think in these type of terms that you are going to draw something, right, and beat the definition. You can't. The Q has to be exactly on the line. It has to be a point of this boundary. And then, no matter what disk you draw, and how big or how small, there will always be a point in and a point out. And that's why it's called boundary point. It's on the boundary. Where the interior one, again, you can draw a larger disk, you can draw a smaller disk. All of the points are always inside. Now, yeah, you can draw this disk as well. But that disk doesn't really contradict the definition at all, because it says that, which means that it's possible to find a disk centered at P that contains only points of R. All of these points over here are in R. Everything. So we're good. But this one has to have points that are inside the R and points that are outside of the R. And that's the part where you know it's a boundary point. Two more definitions for open and closed set. A region is open if it consists, okay. So a region is open if it consists entirely of interior points. A region is closed if it contains all of its boundary points. Just think of a store being open or closed. If the store, and let's use the box, right, and there's the door right here to go in. If the door is open, you can walk in and you can occupy any point of the space inside. Open. Closed contains the walls as well, you can't get in. Closed is everything inside and the walls. The door is locked and you have no skills, which means closed. Done deal. It's very, very simple idea. All right. So neither these definitions, we'll look at these again. So let's take a look at some of these problems that are the limits at the boundary point. What kind of boundary point? Well, these kind of, jumps of the function. And you have these straight drop vertically down and so on. But again, you immediately know these problems because once you plug in, you get those dreaded zeros in denominator. So we have x plus y squared divided by x squared plus y squared. So there is a very cool trick to deal with these types of problems. And that is converting this Calculus 3 problem into a Calculus 1 2D problem by just writing down whatever relationship between y and x you want to have. Let me remind you that your domain is a 2D domain in which Calc 1 limits live, right? The point 0, 0 in this case is the origin. And if you are to put the line y equals x like this, then that restricts your motion through space, and you can approach from this direction or from that direction. And you are approaching along this line. Now you are going to get hopefully a number. I don't know, say 7. And then you change the line. You redo the same problem for a different line, saying y equals negative x. And then you approach from two sides. You approach from one side, you approach from the others. Again, these are not left and right, they're just right. Now look at this. If you compute 7 using this approach, that means that this point is on elevation 7. But if you have a different approach, which is along the other line, and you get elevation 3, well, 3 is not the same as 7, so the paths did not agree, therefore there is no limit. And now it's time to actually look at the edge of this desk. If I am to approach an arbitrary point over here, right, this one, let's say, if I'm to approach along this edge, so I'm approaching, and guess what? If this is 4 feet tall or 3 feet tall, whatever it is, the answer would be 3. But then I decide to have an approach that goes perpendicular to it. So half of this approach is walking on a desk, but the other half is walking on the floor. Now that one will have no limit, because one will give you 0, the other one's giving you 3. So you see that it matters which way you approach the point at the edge. So now what I'm going to do in this particular case for this problem is I'm going to make the assumption that, not the assumption, I want to use the path y equals x. So that is me walking on y equals x. And now, as you can see, I replace all y's with x's. And let's see if that helps. So what do I get? I get now limit x goes to 0, right? Because your y is x, so you have x comma x goes to 0 comma 0. So just call it x goes to 0. On top, you have 2. So let's just plug everything in. You have x plus x squared divided by x squared plus x squared, because each y is equal to x now. So just plug in. And what you get is the limit x goes to 0. You have 2x everything squared divided by 2x squared. Now that is 4x squared divided by 2x squared, and the whole thing is 2. So the z value, as you approach 0, 0, in this fashion is 2. Now, I'm going to use different blue, this one. Use the path y equals 2x. So all I've done is now I am coming up with another line that it's 2x. If I get a different value for this, then there is no limit, because you can't have the limit if you have different paths give you different numbers. Just like your Calc 1, left limit and right limit must have the same value if you are to have the limit. If they don't have the same value, no limit. So now I am changing the approach, but instead of going from left to right, now I'm actually changing the line on which I'm walking. Guys, I could have picked parabola, right? If the limit existed and if the 2, no matter which function you pick, go ahead and use e to the sine x if you like pain. You would have to get 2 if the limit is 2. But if you get anything else, the limit does not exist at that point. So let's do this calculation now. I have limit, again, x goes to 0. And now each y is replaced by 2x, so I have 3x, everything squared on top, divided by, and then on the bottom, I have x squared, which I'm copying, plus 4x squared, because y is 2x, and when you square it, you get 4x. So what is the limit over here at the end of x goes to 0? Okay. Right? We have 9x squared divided by 5x squared, and it's 9/5. So 2 is not the same as 9/5, and that's the reason why the limit does not exist. So limit x plus y, everything squared over x squared plus y squared, does not exist. So that's xy going to 0, 0. So I was able to find a different path that gave me a different number. And that's all to it. Now, you've seen me use y equals x and y equals 2x. I could have saved myself a lot of trouble in this problem if I used y equal mx, because I can do one calculation only. Green, I guess, because that's the way to do the problem, right? The efficiency, green. Eco-friendly way, less paper, less pencil, less, right? You use less calories, which means less food, like everything is less. So green. Instead of fixing value, instead of y equal x, y equal 2x, and so on, pick y equal mx, right, for mx plus b, y equal mx, and then plug that into your problem. Let's see what happens. So I have this, and now I have the limit, x goes to 0. We have x plus mx squared divided by x squared plus mx squared. Right, it would used to be x plus y, now it's x plus mx, because y is mx. Follow the algebra. Limit x goes to 0. In the numerator, we have m plus 1 squared x squared. Because you factor out x, right? You factor out x, you get x times m plus 1, and then you square each one of these. And in the denominator, you get to square first, so you get x squared plus m squared x squared is just algebra. And now you have m plus 1 squared x squared divided by, factor out x squared, you get 1 plus m squared. And this is where these guys die, x squares. So what are you left with? You're left with m plus 1 squared over 1 plus m squared. You see, the answer depends on which m you pick. And that is why this is the most efficient method to use, rather than, guessing. Because, what happens if it holds for a few of these and then it doesn't hold for the 7th one you try? Well, you wasted a lot of time. So using general case, mx, this is checking for infinitely many approach, right? Because m can be any slope. And as simple as is if your answer is m dependent, then no limit, right? So here in green, the answer depends on m, right? The answer depends on m, and it just depends on m, implying limit does not exist. That's all it is, because you have a different approach and you're getting a different z value back, and we know that you can't have that. So the two-path test for non-existence of functions is if f of xy approaches two different values as xy approaches a, b along two different paths in the domain of f, then the limit does not exist. That's technically what I wrote here in green. Not all problems, maybe I should write that here in blood. Note, cannot use y equal mx in all problems, or for all problems, for every problem. There you go, for every problem. Cannot use that. Sometimes try y equal x squared, y equal m x squared, y equal e to the x, right? So try other functions, because your linear function might end up check out for m, but then you try quadratic or you try exponential or something and it just dies. So do not limit yourself to y equal mx. When you try a few homework examples, it'll be clear. Continuity. Class ends like 10 p.m. something. We have time. So continuity is the last part of this lecture, and it's going to be the same definition as in Calc 1 adopted to the Calc 3 two-dimensional domain input, right? So if you remember your Calc 1, function value has to exist, limit has to exist, and they have to be the same. That was Calc 1. Now I'm going to write the same thing in Calc 3. So, definition, z equals f of xy is continuous at AB if. And here are the three things. Number one, f of AB exists. This is the pre-calculus. You plug in the numbers, and if you get a number out, pass. If you get infinities or can't compute, then fails. Number two, so the limit of f of xy exists. So if you approach AB and the limit exists, you're good to go. Three and final, limit has to give you the f of a b. So it has to produce that answer. So absolutely same stuff as in Calc 1, except now it's in 3D. Clearly we're going to take a look at a few wonderful examples. And then the continuity propagates the same way as you go. Now let's see, I'm trying to find, okay, fine, there we go. I don't know, let's do whatever, 38, whatever. Unless you want something else. So continuity at the point. So we have f of x, y, which is a z, right, is given to us as x squared plus y squared divided by x y squared minus 1. Can anyone tell me the quote-unquote bad points? Yes.
X equals 0 and then y equals 1.
0 and 1, yeah. 0 and 1 is a bad point. Here, bad point. Why is that a bad point? Why'd you pick that one?
Because I killed my father when I was little.
I knew it. I was just waiting for it. I was just waiting for it. I know it too well.
Makes the denominator 0.
Makes the denominator 0. Very good. Another one. 0, negative 1. Also bad point because it will also create 0 in denominator. Now, how many bad points do we actually have here? The answer is infinitely many. Would you all agree that any combination of 0 in x and whatever on y will create 0 in denominator? And any combination of x being whatever and having 1 or negative 1. Do you see that? Mm-hmm. That's a lot of points. That's a lot of points. This poor function has no chance at continuity, all right? No chance in continuity whatsoever. There are infinitely many points that create these zeros and denominator. Okay? One blanket? You good? Ah, fine. Oh wait, you went to the trip, right? Oh, so those are the effects. I know it's long hours on a bus. It's not easy. Anyway. All right. Good. So we can test, right? If you pick this point and you plug this point in, the function value does not exist. Right? So immediately this continues because rule number 1 failed. And you keep keep picking points like that. So any combination, so bad point, or any along lines x equals 0, y equal -1, y equal +1. So there are these three lines in the domain along which you are going to have this. Now, I'm unfortunately, Mathematica makes my computer explode, so let me try and see if I can graph this. So I'm typing all of this in the Mathematica. And we're just going to display the graph. If you're listening that at home, then you should be graphing this in Mathematica to see. Let me see. Yay. Beautiful. It's beautiful. Unfortunately, can't zoom in because we need the Pro version. Look at it. How continuous is this? I know, right? Now, hopefully you see x equals 0. You see that? And here are your y1 and -1 lines. And you see it has these vertical cliffs at those numbers. And then the rest bends around it. That's what you would call a bad hair day, right? So for continuity, you have the same rules. And then the global continuity is going to be the same as in Calculus 1. If the function is continuous at every point, it's globally continuous and the entire region R. There are infinitely many points, so you got to check each one of them, right? Which is very inefficient. So we'll learn that certain surfaces are globally continuous. And then we also have the, piecewise continuity. The book doesn't really go into all of these details. They went actually more in detail in Calc 1 and Calc 3. But, there are certain parts that are continuous. You can, climb up certain parts, and then they will just fall off on other parts. Another definition that we want to consider here would be the definition for a continuity of multiple functions. So what you learned in, well, they don't put it here, but what you learned in Calculus 1 is that if you add and subtract or multiply or divide continuous functions or square them, you are going to get the continuous function. Division is a little bit tricky. You have to make sure that the denominator, right, is not 0, because that would create discontinuity with the division. But if your denominator is, let's say, x squared y squared plus 1, you can't really make that 0, right? No matter what you put, those squares will always give you the positive number, and then you add 1. So the denominator is at least 1 every time. There's no way to make it a 0 or a negative. So for that matter, you can have a situation where you are dividing two functions and it's still continuous. So, you know, whatever seems to be continuous in your head should be continuous. You know, polynomial-like stuff. I believe your problem 31-ish or whatever was something along lines z equals to, you know, 3x squared plus 4xy minus 9. Well, that's a polynomial-like problem, and this has to be continuous everywhere, right? Because there are no vertical lines that would make those cliffs, right? There's no denominator equal to 0. There is no ln to ruin anything for us with its vertical asymptote at x equal to 0, so, or y equal to 0 for that matter. So, you know, so let's say that this is your, instead of z, let me put f of x, y, and let me come up with the g of x, y as I said, x squared, y squared plus 1. So I would say this one, continuous, this one, continuous, and then f plus g, also continuous. It's continuous because, yeah, I don't have any like terms other than negative 9 and 1, but still, all of the individual parts are, you know, quote-unquote polynomial-like, so yeah, we're good to go. F minus g, the same thing, continuous. If you multiply these guys, you get also continuous. Now, I said division is tricky. If you divide these guys, well, I'll put in parentheses, need to show g different than 0. And that's easy, because x squared, y squared plus 1 is different than 0. There are no values, you know, under the sun that you can put for x and y in as real numbers to get 0. So because that's true, again, continuous. What else is continuous? F squared, right, or g squared is continuous. Again, does not introduce vertical asymptotes, right, which would create those vertical drops. But another big emphasis is continuity of composite functions, because that's what we are mainly interested in. Most of the functions we deal with in nature and otherwise are composite functions. So, theorem, it says if u equals g of xy is continuous at AB and z equals f of u is continuous at g of AB, then the composite function z equals g of xy, sorry, z f of g, cramming, z equals f of g of xy is continuous at AB. So a cool question, especially for, you know, donors and so on, but everyone, not a big deal. Say you have z is equal to 3x e to the sine xy. Right? Let's say this is, so is this continuous? Well, the answer is yes, because all of the stars aligned over here. We know that this is multiplication. X on its own is continuous, y on its own is continuous. When you multiply two continuous functions, you get a continuous function. That's the rule number 3 on our, or 2, or whatever it was, on our list of limit laws. Right? Number 4, multiplication, the product of the two. So that's that part. So xy as a multiplication. Now, you have xy plugged into sine. Sine is continuous, xy is continuous, so the entire thing over here is continuous. Now that is with this e. That is plugged in terms of the function composition, which is the red one above. So that's continuous because e to the x is continuous. And then another multiplication with 3x. So you follow from the inside, outside. You have to start with xy, say that's number 1, continuous, and then function composition, continuous, and then another function composition, continuous, and finally multiplication at the end, continuous, and you get that argument all the way. So I said this maybe 5 times, which excuses me for writing, so I'll just say write-up goes here. Continuous, yes. Start from xy, go into sine xy, go into e to the sine xy, and finally go into 3x e to the sine xy to show that it's continuous. Functions of 3 variable, 4 variable, 5 variable, just use more letters. Same rules. And that's it. I hope you're not disappointed. And we'll take a short break. When we come back, partial derivatives. You'll be on waiting for that one for a very long time.